Welcome at Eindhoven University of Technology. Good to have you back at the second RILEM International Conference on Digital Concrete. I hope you all enjoyed the first day of the conference and that you were able to have a good learning experience and meet your peers and, of course, our sponsors. Today we have a full schedule ahead of us again, and let's wrap up that thing for you that is upcoming today. We start with 2 keynote lectures, and in between we have the second episode of our series on Science Meets Industry, a series where we would like to showcase how technology from our university is being transferred to the industry here in the Netherlands. After that, we have a break, and after the break, we have a long series of parallel sessions. Like yesterday, again, 4 parallel sessions where we can hear a lot of things, 32 presentations on the field of digital concrete again. After that, we have a second, that's our third episode on Science Meets Industry, and everything will be finalized with the wrap-up. And we are looking forward to see Laurie Haas here for the first time appearing in our conference on this stage. I have a couple of messages that I would like to make before we start with the program. The first is that please have a look at the virtual booths that our sponsors have established. You can find them in the sessions page of our Hopin platform. Please scroll to the bottom, so they're just below the mentioning of the rooms A, B, C, and D. Another thing I would like to mention is that proceedings are available, and you can find them in the reception area of the Hopin platform. And another issue is maybe important for you to tell that some of the presenters have received a message, of all of them have received a message, to come in via Zoom and meet us and be able to do the Q&As. If you are a presenter today and you did not have received the invitation for the Q&A, please message that to us, digitalconcrete2020.com. Yesterday we had one technical issue, and unfortunately the presentation of Juliet Beckering was not running well. So we have rescheduled that session till Wednesday between 14:30 and 14:45. So for those who want to see that presentation, please bear that in mind. And for all of you count, and I think it really matters that during these presentations, you can always in the chat box matches your questions. Yesterday, it was really active on the chat box. Many questions came in, and that's really good to see. As well as the breakout sessions, where we met a lot of people just discussing the issue of digital concrete together. So please, again today, make use of these opportunities to meet your peers again, I would say. There's only maybe a final message, and that's more or less a message to one person. I would say to Robert Flatt, sorry for the introduction movie. We couldn't change it today that rapidly, but chemistry, I fully agree with you, is key. And with that message, I would like to start with the program. And the program brings us to the first keynote presentation. And the first keynote, and it's a pleasure for me to announce that, comes from Professor Leuke. Professor Leuke is an expert on colloidal interaction, rheology, processing, and durability of concrete, as well as the technology of high-performance concrete and additive manufacturing. He studied civil engineering, and during his PhD, he studied the field of robustness of self-leveling concretes. From 2006 until 2017, he was the head of concrete technology at the Center for Built Materials at the Technical University of Munich in Germany. Since 2017, he has been the head of the Department of Building Materials at IBMB of the Technical University of Braunschweig in Germany as well. In between, in 2016, he was a research scholar at the University of California, Berkeley in the USA, doing research in the field of 3D printing with cementitious materials. He is also the deputy chair of the RILEM Technical Committee, Digital Fabrication with Cement-Based Materials. Dirk, Professor Leuke, a warm welcome to our conference. It's a pleasure to have you here and an honor as well.
Thank you, Theo, and welcome, ladies and gentlemen. The pleasure is all mine, and I'm really honored to be speaking here today.
If I read the title of your presentation, Professor Leuke, it is all about particle bed 3D printing. What we heard yesterday was something different, a series of wonderful presentations, but on a different aspect, on a different theme, much more on material deposition, more about extrusion or pouring in very thin molds. You do something different, and I really look forward to what your thoughts are on the characteristics of particle bed 3D printing, its advantages, and the state of the art to start with.
Indeed, too, I believe particle bed 3D printing is somehow different, but before I start, I'd like to mention my co-authors. Inka Dressler, she's senior researcher at my group in Braunschweig, Daniel Vega, Daniel Teike, and Christoph Gielen from Technical University of Munich, and Friedrich Herding and David Böhler. These two are PhD students in my group, and they are working on particle 3D printing. Let me start with a brief outline how particle bed 3D printing is classified in the vast number of today's additive manufacturing processes. With regard to concrete structures, we can distinguish between three main AM technologies. On the left, you can already see the open space techniques where the concrete is deposited by either extrusion or by spraying. And when we are using these deposition techniques, we firstly have to mix cement, water, and aggregates, and subsequently we extrude or spray the concrete and form the concrete element. The alternative I want to talk about today is the particle bed 3D printing or particle bed binding, where we selectively bind the particles in the particle bed. Here in the first step, a layer of dry particles is spreaded, and subsequently a liquid is selectively applied onto the particle bed in order to locally bind the particles. After finishing the printing procedure, then we have to delose the non-bounded particles from the particle, and finally we have built up our concrete element. If we now have a closer look on the particle bed binding techniques, we can at least distinguish between three methods which are considered to be relevant in concrete construction. Firstly, the selective binder or selective cement activation here on the left side. In this technique, the particle bed consists of aggregate and binder, which could be a cement, for instance. And the fluid phase is the activator, which could be simply water in the case of the cement as binder. Then we have the selective paste intrusion technique, where the particle bed consists of an aggregate layer, and the fluid phase is a very flowable cement paste. And on the right-hand side, the binder jetting method, where the activator is in the powder and the binder is the liquid phase. In the context of concrete construction, the latter can be used for the fabrication of formworks, while selective cement activation and selective paste intrusion allow the direct production of concrete components. And today I will focus on these two techniques. So why should we use particle bed binding techniques? What are the advantages compared to deposition techniques? Particle bed binding offers a very high resolution and almost no restriction in freedom of form. Among the various 3D printing techniques, particle bed binding offers the largest freedom of design. Since the dry particles are mechanically stable, inclined structures, overhangs, arches can be easily realized. Here you can see some very impressive results and examples. On the top left, the permeable wall from Ronald Rell from UC Berkeley with his really stunning surface quality. On the right, on the top, you can see some highly precise dry joints to realize, for instance, the load carrying connection of a truss, which were produced at Technical University of Braunschweig. And on the bottom right, an extremely freeform, bionically optimized column cross-section produced at Technical University of Munich. However, there is a major drawback on the particle bed binding techniques, and this is the limitation in the component size, which is limited by the build space. And another disadvantage could be that we have the need to recycle the unworn material of the particle bed. Okay, let's move on now to the mechanical performance. For selective cement activation, the strength values without after-printing treatment do not exceed 17 megapascal. If an after-printing treatment is applied, you can see this here in the blue columns, then strength values can reach up to 34 megapascal. The level of strength is within the expected range, as these concretes have a density of approximately 1.6 gram per cubic centimeter, and therefore they can be classified as lightweight concretes. In contrast, the selective paste intrusion here on the right side achieves normal densities of about 2.3 gram per cubic centimeter and correspondingly a significant higher strengths of up to 78 megapascal so far. And finally, I want to address the isotropy of these materials. And therefore, in this graph, the strength is shown perpendicular and parallel to the layer structure. And as you can see, the current experience show that no directional dependence of the material properties can be observed for the particle bed binding process.
Thank you for this nice overview of the state of the art and the potentials of particle 3D printing techniques. In your title, you also seems to tell that the technology, in your perspective, in your view, is capable to work in the construction field as well. So that would suggest you need to upscale to another level, and there must be a certain level of trust on the materials properties that you achieve with this technology. Could you please elaborate a little bit more on your suggestions, your ideas on how to scale up this technology to the field of construction works?
Yeah, I will do here. Firstly, I would like to follow up on Robert Flatt's statement yesterday. In order to establish additive manufacturing processes as a serious technology in the construction sector, we now must develop a deep and fundamental understanding of these processes. This means that future work in research and also in industrial development will be characterized by creating the basis for the reliability of these processes and the repeatability of these processes. I believe simply demonstrating the basic feasibility of a process will no longer be sufficient. And in order to do that, in order to improve, for instance, the mechanical performance on the one hand and the repeatability of these properties on the other, we need to understand and optimize every single sub-process of particle bed binding processes. And here we have firstly focus on the particle packing, where we have to consider, of course, the chemical nature of the particles, the particle size distribution, as well as the spreading and the compaction process. Secondly, we have to focus on the liquid phase. Here we have to consider the rheological properties of the liquid phase, the properties of the particle bed, as well as the process parameter. And in this context, it is essential not to consider the influence separately. It is rather necessary to capture the interaction between the material and the processes. Material and process in turn affect then the homogeneity, the stability, or the layer bonding of these additively manufactured components. And thus, its mechanical properties and, for instance, the shape accuracy. And last but not least, if we intend to apply particle bed binding for the fabrication of large-scale components in concrete construction, we have to address the issue of reinforcement integration. Let me firstly address the selective cement activation technique. Here we start with the particle bed spreading process, and from process technology side, we have a wide range of tools at our disposal. Usually, doctor plates or rotating rollers are applied for the particle bed spreading process. These tools significantly affect the packing density, the surface quality of the particle bed, as well as the number of particle percolation paths. And we could see in the state of the art, for instance, that components manufactured by the selective cement activation are characterized by a low density and strength. Thus, to increase the density and the strength, we have to increase packing density of the particle bed, as well as the number of percolation paths. One way to achieve this goal is to adjust the layer thickness or the roller diameter. And as you can see here in this diagram, the density, for instance, increases with increasing layer thickness and increasing roller diameter. I believe that increasing the packing density of the particle bed is the key to increase the density and the strength of our components. Therefore, the focus of future research should be particularly placed on a specific compaction process of the particle bed process. Let me now continue to the process of liquid application. Here you can see the different patterns of liquid discharge from a nozzle depending on the applied pressure. Within the framework of a recently started research project, we are studying this phenomenon specifically for fluid application setup at the selective cement activation process. This project is a part of the recently started collaborative research center TRR 277 on additive manufacturing and construction, which was established at the Technische Universität Braunschweig and the Technical University of Munich. And if you look in the bottom line, you will find the logo of this CRR TRR 277 AMC. And we would really appreciate if you would visit our homepage, of course, after this presentation. Okay, let me start to show you some slow motion videos of the liquid application process. Here we use the 220 micrometer nozzle and the flow rate of 3 millimeter per minute. And in this scenario, the water appears as small droplets on the surface of the particle bed. If you now let's have a look on a second video, here we just increase the flow rate up to 10 milliliters per minute. And you can see that the breakup length increases and the water now forms a continuous water jet. In the last scenario, we have now increased the diameter of the nozzle to 625 micrometers while maintaining the same high flow rate of 10 milliliter per minute. And now you can see the water again from droplets, but now with a larger diameter. As you can see, there's a complex relationship between nozzle diameter, flow rate, and the shape of the water jet. But if you now express the flow rate and the nozzle diameter as a flow velocity, we can see that there's a functional relationship between flow velocity and droplet size. With increasing flow velocity, we can see a decreasing droplet size. Furthermore, we can also identify a flow velocity at which there is a transition from a droplet shape to a continuous water jet, in our case here, at 1.5 meters per second. Well, this knowledge is now the starting point for the next sub-process, the impact and penetration of the water into the particle bed. Let me start here with the effect of the outlet velocity and the particle size on the roughness of the particle bed after the water has impacted the surface. Here we use the digital microscope to characterize the surface texture. And for the sake of simplicity, we have defined the maximum pit depth as the characteristic value for the surface quality. And as you can clearly see in this diagram, with increasing outlet velocity, the maximum pit depth increases. However, if you use coarser particles, as you can see here in the gray symbols, then the particle bed, so if we use the coarser particles in the particle bed, then we can really attenuate this effect. Ladies and gentlemen, now we will have a closer look on the water intrusion into the particle bed. Here you can see how a water droplet hits the particle bed and intrudes into the particle bed. In real time, this process takes about 0.25 seconds. And in these investigations, we are interested in the intrusion velocity and how we can control the intrusion behavior into the particle bed. In the first step, we focused on the effect of particle size and mixture proportion. And therefore, we investigated mixtures of cement and 3 types of aggregates, namely a fine, a medium, and a coarse quartz set. And as you can see here, the intrusion velocity increases with particle size. In the second step, we write the ratio of cement to aggregate from 20 volume% cement and 80 volume% aggregate to a ratio of 40/60. And you can see with increasing cement content, the intrusion velocity significantly decreases. This concrete technology variation corresponds to what we actually expected. However, the variation of cement content and particle size is not always an option. So we are looking for further ways to control the penetration behavior. And one really promising way to do that is the coating of particles. Therefore, our co-workers from the Institute of Particle Technology coated sand particles with a hydrophilic silica fume. On the left side, you can see the uncoated sand particle, and on the right side, there's the coated sand particle. And now let's see how this coating influences the penetration behavior. Again, on the left side, the uncoated particle, on the right side, the coated particles. And you can see, firstly, that the sand particles somehow moving on the surface of the water droplet. And if we further on the video, then we can see that the intrusion velocity significantly decreases when the sun particles are coated with an hydrophilic silica fume. In terms of numbers, the penetration rate is halved from 34 microliter per second to 17 microliters per second. The next important characteristic is the intrusion depth. Since the complete penetration of the layer with the fluid phase is important to achieve a good layer bonding. To quantify this impact or to quantify this important characteristic, we used microtomography in this case. In these pictures, you can see the intrusion behavior independence on the particle side. On the left side, there are the finer aggregates, and on the right side, the coarser ones. And you can see that somehow, at least for us, unexpected result that the intrusion depth is larger for fine particles than for the coarse particles. Okay, if you now plot these results as a function of particle diameter, we see a clear trend that the penetration depth decreases with increasing particle size. At the same time, however, the ratio of width to depth increases too, which indicates that the water is increasingly distributed horizontally as the particle size increases. I would now like to change the viewing angle slightly away from the observation of the individual mechanism to the macroscopic properties of the components. And to do this, I will start with a video showing the inner structure of a specimen manufactured by selective cement activation captured by micro-CT. You can clearly see the layered structure caused by the manufacturing process. And to quantify these properties, we used the grayscales of the micro-CT images, as you can see here, to calculate a homogeneity factor. And the lower the difference in grayscale between each layer or between the layers, the higher the homogeneity of the cross-section. And here, exemplarily, you can see some of our results. If you're interested, please have a closer look to our paper and the recent special issue of Cement and Concrete Research. But what you can see here is the effect of water-cement ratio as well as the effect of water jet pressure at the nozzle on the homogeneity of our specimens. And we can see with increasing water-cement ratio or decreasing water jet pressure, the homogeneity of the specimen significantly increases. This graphic should demonstrate that we are able to control the homogeneity by means of concrete technology or process technology parameters. Okay, let me now briefly say a few words about the selective paste intrusion method. In the selective paste intrusion method, the particle bed consists of a granular sand, and the selectively applied fluid is a cement paste. Recently, together with my colleagues Norman Hack and Harald Kloft, we have scaled up this concept to particles with a diameter of more than 30 millimeters. In this case, the fluid phase was a fine-grained shotcrete. And as you can see, the first results are quite promising in terms of mechanical strengths, because the printed structure can easily carry Norman's weight. I'm sure you will see more from this in the coming months. So what is the main challenge on selective paste intrusion or selective shotcrete intrusion? It is similar to the selective cement activation technique, since the fluid phase has to completely penetrate the layer thickness to ensure a proper layer bonding. It was recently shown by Daniel Weger and co-authors that compressive strength increases with increasing penetration rate. To investigate the penetration behavior of the cement paste, you can perform simple penetration experiments and again use the micro-CT to quantify the results. Here you can see some examples. On the left-hand side, you can see how you can determine the penetration depth of the paste or the mortar. But with the aim of the computer tomography, we are also able, for instance, to quantify the packing density of our particle bed, as you can see here on the right-hand side. This is also a project which has just started, and the aim here is to numerically simulate the paste intrusion in the particle bed. And hopefully, we will see some results in the coming months. In recent years, this process was intensively investigated by Daniel Vega, and you can see some results of his work here. The aim of his work was to connect the rheological properties of the cement paste with the penetration depth in an analytical model. And this diagram shows results, and you can clearly see here that, as expected, the penetration depth is increasing with increasing flowability of the paste. And you can see his final model on the right-hand side, and this model is based on the Chevalier model, and it captures the yield stress as the main characteristic for the fluid phase, as well as the porosity as the main characteristic of the particle bed. Furthermore, his model considers the horizontal flow of the cement paste. And by doing so, the model is able to predict the penetration quite accurate, as you can see by comparing here, for instance, the green symbols with the white ones. If you're interested in further insights on this topic, I recommend the PhD thesis of Daniel Vega, which will be available quite soon.
Thank you, Professor Leuke. Having addressed the issue of scaling up in terms of size and in terms of achieving reliable material properties, I think we need to discuss a little bit more the issue of reinforcement. I think there's no need to explain in this audience that concrete is good in compression, but really poor in tension, and that the marriage between one material and the other is part of the success. What is your opinion about the opportunities with this novel technology to embed reinforcement to really make that jump towards the construction industry and have a serious impact?
Indeed, as for other 3D printing techniques, the integration of reinforcement is one of the main challenges in particle bed 3D printing. In principle, there are at least 3 strategies for the integration of reinforcement for particle bed binding techniques. Firstly, here on the left side, you can integrate a metal cable during the printing process, which could be a good method for the integration of horizontal reinforcement structure. Secondly, in the particle bed 3D printing process, you can easily print cavities into the concrete element. And after the concrete element is printed, then you can introduce a reinforcement into these cavities, make a post-tension and grout these channels. We are addressing these 2 strategies in a research project that has recently started within the framework of the Collaborative Research Center TRR 277 AMC. And yeah, hopefully again, we will present our first results quite soon. But a third very interesting strategy is the simultaneous manufacturing of steel reinforcement by wire and arc additive manufacturing. This strategy is pursued for the selective paste intrusion method at the Technical University of Munich, also within the framework of the Collaborative Research Center TRR 277. And in this process, the reinforcement is built up section by section before the printing of a concrete layer. The main problem, however, is the heat generated during the welding process. The temperature at the welding point exceeds 1,500 degrees Celsius. However, as you can see in the picture on the right side, preliminary tests show that by moving the weld point out of the particle plane by only 25 millimeter, the temperature load in the particle bed can be reduced to around 100 degrees Celsius without any further active or passive cooling strategies. So if you're interested in this special technique, then I refer to the presentation of Daniel Vega on Thursday in room D. Let me now conclude my talk. I believe particle bed 3D printing techniques are applicable in concrete construction. The main advantage of these techniques are their high resolution and the fact that they have almost no restriction in free form and the freedom of form. For the selective paste intrusion technique, we have already very good material performance. In the case of selective cement activation, the density is about 1.6 gram per cubic centimeter, and therefore the strength is similar to lightweight concrete. To further improve the reliability of these techniques and the repeatability of the material properties, basic research on the interactions between material and process is needed, which I addressed in my talk. I think the most important are particle bed spreading and compaction process, the liquid application process, the liquid intrusion process, and the modeling of these processes. And last but not least, we need strategies, of course, for reinforcement integration into the particle bed. Finally, let me close my talk with thanking my group for the excellent work over the past years, and now I would be glad to answer your questions.
Thank you, Professor Leuke, for this wonderful presentation, in particular the state-of-the-art overview that you gave us and would like to share with us. I'm with you that we can have a look at the questions that came in on the chat box, and some of them are closely related, of course, to the theme that you discussed on how to bring the technology to the industry. The first question on this topic is questioning that if you're aiming for an industrial implementation, would it be possible to reuse non-activated cement in this technology again?
Of course, that's a very important point if you want to apply this technique in industrial applications. And we did not or no systematically investigations so far. But what we know is that we can at least reuse the materials for 3 times. But this is certainly a point we have to look to have a closer look on it. But I believe we can for the cement activation method, and of course for the selective paste intrusion method, there's no bigger issue because this is only aggregate and we can reuse it.
Thank you. There's also a question in terms of costs, in particular on the issue of nanomaterials. To be more precise with you, nanosilica is an expensive material and also could cause some issues related to health and safety. The question is if there are any other materials available that could replace this material.
I think you mean the silica fume.
I mean the silica fume, yes.
Yeah.
I think
Actually,
the question is about the silica fume.
As I told you, it's not. We just started this project and we try other materials for the coating process. I will present these results as soon as they are available, but today I cannot give you an answer on that. But we believe this is a technique which could be beneficial for this process, and we don't believe we have to coat all the particles, but for instance, one fraction of the particles to control the liquid intrusion.
A more technical question came in, and that's it's on the penetration. So, and the question is, could you comment on the scatter in penetration behavior of the droplets? Is that highly constant, or are there variations observed in your research?
If you use the same material and the same fluid application techniques, then we have a quite good repeatability between the results. But as I've shown, if we vary the materials, then we have a big scatter and a big variation in the intrusion method. But that's not a disadvantage. I see that as an advantage because this is the way we can control the intrusion behavior. Okay,
well understood. Another question, again, more in-depth on the technology. It's about interfaces and mechanical characteristics. And the question actually is there any insight to share from you already from your ongoing research work about the mechanical characteristics of what is so-called interface versus the bulk printed material penetration and the relationship with the discussed penetration depth?
Yeah. So here we have to distinguish between the selective paste intrusion and the selective cement activation. In the selective paste intrusion, there's a strong relationship between the intrusion depths of the cement paste and the mechanical and the durability properties. There are some publications from Daniel Vega and co-workers where you can see these results. If you are looking for the cement activation, selective cement activation, then I would like to recommend our latest publication in the cement and concrete research issue, in a special issue. And what we found somehow surprising for us, our hypothesis was that we can relate homogeneity of our structure with mechanical properties, but not what our results show that this is not the case in any case, because there are other parameters who can dominate the homogeneity property. So this is an important property, but not the only one who is affecting the macroscopic properties. So please read our journal publication. I think it's very interesting on this point.
Talking about homogeneity, a closely related question to this issue matter came in, and stating that homogeneity of the samples estimated by means of tomography is considered as a benefit. And the question is, while it seems that with a rougher interface profile, a better mechanical adhesion between individual layers can be achieved. Do you agree on that point?
I would like to. This is our hypothesis too, but we have not validated it so far. But we will do this. Actually, as I told, we started the project. It will last for the next 4 years, so we have a lot of time and manpower to give you all the answers. But I think we need another year for this.
Thank you very much, Professor Leuke. This brings us to the end of this keynote, and I would like to thank you on behalf of all of us very much for this wonderful presentation, this insight, that state-of-the-art overview in this novel technology, the different technology, I would say, and I think we all learned a lot today from that, and that is highly appreciated from all of us here. If there are many more questions, and there are many more questions that you would like to raise to Professor Leuke, what I propose is that after the second keynote, we all meet in room A with you, and I kindly invite you and all the others to be there and meet your peers and discuss the issue matter any further. Okay. Thank you again, Professor Leuke, for your presentation.
It was my pleasure. Thank you.
And this brings us to the next part, and that is the second episode of Science Meets Industry. And that's a part that we are going to use to showcase what we are doing with all the technology that's being developed here at Eindhoven University of Technology in our industry. And that's typically where this area of Eindhoven in the Netherlands, that we call the Brainport area, is famous about, bringing technology to the industry. Welcome at Eindhoven University of Technology. Normally our campus here behind me is crowded with 15,000 students, particularly in springtime like this. Unfortunately, due to COVID-19, it's empty now and we can't meet here together in person. At Eindhoven University of Technology, we develop knowledge related to the issue matter of digital concrete. Sometimes in isolation, in case of fundamental research, but mostly in close collaboration with the industry. Eventually, all this knowledge should find its way to the industry to accommodate an architectural degree of freedom in design, sustainability, and a higher construction productivity. Today, we're going to visit the housing project here in Eindhoven, Project Milestone.
We are here in Eindhoven, in the city district Meerhoven-Bosrijk, and we are here on the construction site of the first 5 digital concrete houses. And people are really gonna live in these houses. We started cooperation with the 5 parties: the Technical University of Eindhoven, Eindhoven Municipality, Witteveen and Bos, that's engineering of the house, Weber BMX, they're gonna print the house, and Van Wijnen, we are the building manager and we're gonna build the house. We had different meetings about the building, the structure and the design of the house. And it's very special that we now have the permit to build the first 3D concrete printed house. The design of the houses is made by Hubbe van Mierlo Architecten. There are big stones, menhirs from Asterix and Obelix, and they are landed in this field. We are using a parametric model, and we made the design of the house in it, and also it's the structure of the house. So we can send it to the robot and we can print with it. For this project, we don't use a steel wire in the concrete element. We have a special design of our house, and we made a structure that we don't need a steel wire. Let me explain the structure of our house. We're first making the piles in the ground. That's the first part of the foundation. And after that, we are making the slabs in the concrete print factory of Weber BMX. And that slab, that's for transportation of the wall elements and also the second part of the foundation. On that slabs, we're going to print the wall elements. And after that, we transport them to the building location and we put them on the piles. On the wall elements, we put a wooden rooftop, and on the wooden rooftop, we put the parapets. And it's also from printed concrete. For the first house, we use a rooftop from wooden beams. It's actually a traditional way of building. For the next houses, we want to use a prefabricated wooden floor, or maybe we print the floors and we put some reinforcement in it. Weber BMX is going to print 5 houses.
Welcome in our print factory that we own together with BAM and Weber BMX. Here we will print the houses for the project milestone. Before we started printing, we had to solve quite a few challenges. One of them being the cantilever of the outside wall, the second one being the long printing time, up to 16 hours for producing the element, the third being the permitting. This place has to be safe because people will live in it, and of course the last one, logistics, have to be solved as well. The answer to solving the challenges is having a robust system. Robust with regard to the printing system, so the mixing, the pumping, the robot, but also a robust system regarding the mortar. With regard to the mortar, we have decided in our product development to stay with ordinary Portland cement as the binder. The drawback of an OPC system is that you have to find a way of being able to stack layers on layers without the bottom layer giving way when you put on a next layer on top. This problem has been solved to make sure that we have modified the rheology so that we get thixotropic characteristics in our mortar. But another benefit of having an OPC mortar is that the rules that apply to concrete, you can extrapolate this to this mortar because a lot of things are known about ordinary concrete. Another thing is when you have a mortar that doesn't harden immediately but that has an open time of about 90 minutes, it's much more easier to get a monolithic structure. That means that the quality of the layer of the interface, that's the layer between the layers, has the same performance as the bulk of the material. That is extremely important when you have load-bearing structures and when you need the permitting that we need for this house. And it's even worse when you have layers adjacent to each other, so not on top, but next to each other. There we have to guarantee as well that the quality of the interface between layers is of the same nature as the bulk of the material. And with this product and with the system we have, we can guarantee that this is obtained. We have a robust mortar, but also we need a robust system. So for the system, we have an silo mischpump from MTech and SMP. We did modify the system a little bit. We changed the water dosing in order to have a more constant quality of the mortar that is being mixed and pumped. And we swapped the rotor stator in order to have a smaller amount being pumped as is being required by the robot. We have an ABB robot on a track, and we have the possibility to print with a round nozzle and with a rectangular nozzle. The drawback of the rectangular nozzle is when you have a print pad that has curves, you will have to make sure that your nozzle follows the curve, and therefore you need another axis of your robot, reducing the reach of your robot. Then we also have an inline quality measurement system to make sure that we guarantee and control the quality of the end product. This sensor that is inline measures the yield of the pump, the viscosity of the mortar, the density of the mortar and the pressure that is being applied by the pump. From the yield of the sensor, we have a feedback to the frequency controller of the pump, guaranteeing that we always pump the same amount of mortar. This makes sure that the layers, when we put adjacent layers next to each other, they are the width as we want them to have, so we have a monolithic character of the interface of the material in between the layers. Then from the viscosity measurements, we have a feedback to the water dosing, helping us in guaranteeing a constant aesthetic appearance of the element that we print. Then of course the pressure sensor is just as an extra quality control issue if we have a problem with the pressure, that the system shuts down and that the whole system does not explode, so to say. One of the other issues we had to solve was, let's say, the logistics, and for this purpose we print on a slab with anchors that we can hoist, so we don't have to hoist from the printed material, we hoist from the concrete that has been casted on a truck and from the truck to the building site. Well, with all these measures we have changed from a proof of concept to a technical readiness level of about 7 to 8. But still, of course, there is room for improvement and making things better. For more details, please see the paper in the conference proceedings, and I would love to see you in 2021 when the house is finished on site.
When this house is ready, we're going to take the learnings from this first house to develop the next houses. So that's smarter detailing, using a better printer technology, and also use smarter processes to build this house and develop this house. The aim for the last house is to print the house really on this location. For digital concrete printing, we foresee development to use reinforcement in the concrete, but also using less material in the concrete and have a sustainable mortar for the future. We have a question for you, academic world. Is it possible to develop a method or a way to print with different kind of materials, so that we can print reinforcement in the concrete, or maybe print a tube for electricity or for water? Is that possible? Thank you for this innovation and good luck with the next steps.
Welcome back to the main stage of Digital Concrete 2020. I hope you enjoyed this episode of Science Meets Industry. My name is Rob Wolfs, and I will be your host for the second keynote of today by Professor Maarten Steinbuch. Maarten Steinbuch is a high-tech systems scientist, entrepreneur and communicator. He holds the chair of Systems and Control at Eindhoven University of Technology, where he is Distinguished University Professor. His research spans from automotive engineering, with a focus on connected cars and clean vehicles, to mechatronics, motion control, and fusion plasma control. He is most known for his work in the field of advanced motion control, as well as in robotics for high-precision surgery. Steinbuch is a prolific blogger, a key opinion leader on the influences of new technologies on society, and he is also a well-known advocate of electric vehicles. We are very happy that Professor Steinbuch is able to join us in person today. Maarten, welcome and thanks for being here.
Thank you, it's a pleasure.
To start off this keynote, you have provided us with a very nice video, which illustrates your field of expertise. Let's take a look.
Proberen het waar te maken van de tandwiel. Van de tandwiel gaat proberen Robodinho aan te spelen. Robodinho biedt zich aan. Zongje opletten. Zongje let helemaal niet op. Wat zeg ik? Robodinho aan de bal. En dan gaan ze proberen hier weer in de aanval. En dan is het, ja, heel goed. En nou draaien. Open doel. Robodinho. Oh, van het tandwiel. Van het tandwiel. Van het tandwiel probeert 3 man verdediging langs. 1 man, 2 man kwijt. Nu nog eentje. Van het tandwiel. Van het tandwiel. Ja, 2-2. seconden op de klok. 2-2.
Well, it certainly is a delight to see a Dutch soccer team score this summer, despite the championship being postponed to next year. Maarten, we've now seen a first glimpse of your research activities. Can you tell us a bit more about your work?
Yeah, the video you just saw was from 2013. It will the World Championships soccer for robots. These robot systems are completely autonomous. So they have a camera, they look around, they determine together their strategy. It's 5 against 5. And this particular game, it was the final match against the Chinese team. And just a few seconds before the end of the second half, we scored the 2-2. So you could see that all the public watching there was jumping up. And then, unfortunately, in the elongation, we lost. So in 2013, we became second. But in 14 and 16 and 18 and 19, we became world champion in this soccer playing game. So currently, we are still world champion in soccer, doing much better than the human team of the Netherlands. Yeah. What I like, of course, are the technical things from this team of us. What I also like about this specific video is not the robots, but the public. And it is like you are watching a real humanoid game. That's really amazing. If you sit there we were sitting there with 5,000 people, grandparents, parents, children, and we were shouting to the robots, shoot, shoot, and they did not react to us, of course, but still. So I think robotics will take a prominent place in our society, not only in interaction with humans, but also for technology. And that's also a sort of a line in my research group that we work both on mobility as well as in robotics with applications, because robots and cars are also becoming sort of similar. Today I'm happy that you asked me to give here a lecture or a discussion with you about how robotics could also enter the building and construction market, because I think technology will be everywhere, but we have to carefully look where it is useful and where it's not useful. But we will come to that in this talk, I think.
Definitely. So, making the bridge towards the construction industry, we are joined by an audience of architects, civil engineers, material scientists from all over the world. Many of those are involved in the field of 3D concrete printing in some way. I can tell from my own experience that when I was a freshly graduated structural engineer and I had to design our 3D concrete printing, many choices were to be made in terms of robotics. And if we look at the state of the art of our industry today, we still see all of those choices still present. Let's take a look at the state of the art of our industry. We often get questions regarding the choice of printing on-site, on location, or in the controlled environment of a factory. Likewise, just like we've seen now, we see variations of gantry systems and industrial robot arms. Maarten, can you reflect on these choices based on your expertise?
Well, I think the most beautiful parallel is with industrial automation. For instance, the automotive industry, it utilizes typical industrial robots like the last one we have seen for outdoors usage. And the reason is that it is not very difficult to reprogram it to do a different task. Gantries are also used, of course. They are relatively lightweight, so I think the productivity can be higher with such an arm, because you can really design the gantry like a lightweight structure. But it might take a lot of time to set it up. So that's why I think for on-site, you might expect that you will get more the industrial type of arm system, the stacked systems. The whole ball game, of course, is accuracy versus speed and productivity. And I think that is where 3D printing maybe seem to promise a lot, but in practice it is quite difficult to find the right business case, because it is taking a lot of time to put each layer there. And if you want to do that with a certain accuracy with a heavy robot arm, and it will be heavy because your printing head is a heavy one in building and construction, because there is concrete and it's heavy. So how to get the right accuracy in combination with high productivity? And high productivity means speed. And if you go to higher speeds, the accuracy locally goes down. It was very interesting in the last part of that movie to see the person, the human, helping the robot a little bit to take some material away. And of course, if things are optimized in the future, I can imagine that help is not anymore necessary, because you could argue if the business case is then not even worse.
Right.
But so the whole ball game is accuracy versus productivity, hence cost. And then I expect that for outdoor usage, it is more and more, standard to use an industrial type of robot. So an arm system robot.
Right.
Yeah.
So in terms of printing on location, construction sites are typically very rough and uneven surfaces. Does that mean we have to do a lot of preparation work before we can move the robot outside?
Well, I can imagine that robot can simply put on a cart, on heavy duty machinery. However, the key thing is, of course, to do the calibration, because you have to know where the end effector actually is. So to do the calibration, you might need some time, but I can imagine that could be optimized also in practice. So once you install the robot, you have to be very sure that where the robot is standing, it will keep at that position.
Yeah.
Because if that vehicle underneath the robot is going to move a few millimeters, you will not find it easy to measure that. So the calibration and the measurements to actually know where the print head is compared to where you want it to be, that's the key thing. So if you measure without errors, then you're in.
Right, measurement is key.
Measurement is key, yeah.
Well, you could also argue that gantry robots have a bigger range because they are so large, but maybe a bit less degree of freedom. And the other way around, the industrial robot arms are smaller, but they can make more complex shapes. So sometimes we see that people put an industrial robot arm upside down underneath the gantry or on top of a rail. Yeah. Is that then the best of both worlds?
Well, sometimes. It depends a little bit on the weight of the robot. If the gantry is not designed for such a heavy robot to be there, then you have to be very cautious, because you will get an error, of course, of the gantry itself, depending on where the robot is fixed. So it could be, it gives you more flexibility, of course, and you can have a huge span. I think if the span requirement is large, then you either have to move a robot arm on a vehicle, on the ground, or you have to use a gantry type of structure, because otherwise you cannot have the reach. There are huge arms, by the way. The biggest Kika I know, I've seen it, it's huge, but it's also very heavy, very expensive. And again, because it's so large, it is very heavy. The speed goes down, so productivity goes down, because if you want to have more productivity, you have to speed up, but then the accuracy is lower. Right. So that's the balance you have to do between accuracy and speed.
Okay.
Yeah.
Well, even if you combine them, then I still sometimes have the feeling that we're copying solutions from other industries. Because like you said, the industrial robot arms are being used in the automotive industry. Gantries are often used in pick-and-place applications. Yeah. So is this the future for our construction industry, or is the ideal construction robot still to be developed?
Well, maybe, it could be. So I would suggest a lot of research just to go into this field and to look. But the key thing starts with what are the specifications. So what is the the range you need, and what is then a practical solution. I think it's good that from your application field you again think again about, okay, what are our requirements and what could be the best solution for us. I don't see many other solutions than gantry or ARM systems, but you never know.
Okay.
Yeah.
Well, let's zoom into the printhead. It was already mentioned briefly just now. During this conference, we've seen many examples of material control or process control at the level of the nozzle, so at the tip of the robot. And the factors are becoming more and more advanced. Let's have a look. So, from a material perspective, we want to have control as the latest possible moment. But as the nozzles in the printhead become more complex, they also become heavier, and we need more active control. Is there a limit to this development?
Well, I think for every application there are, of course, limits. Most important is to think about the measurement system. Again, you want to have accuracy of the printhead, so you have to measure accurately where it is. It's not relevant what the position is of the shoulder. It's relevant where the end effector is. So the more heavy the end effector is, the more heavy the whole chain of the robot should be. And that's doable. You get increased stiffness of the whole structure. However, the mass go up. That means that your speed goes down, and hence your productivity goes down. So that's the balance you have to make. But again, if you can measure, for instance, by optical means, using laser techniques, to measure where you actually are, yeah, then you can, if you move slowly enough, you can compensate for a lot of dynamics and weight. You can compensate via your accurate measurements of the end effector. Yeah.
Okay. So, as these systems become complex, I know that in current practice, most people write their own slicing software, so they program the robot beforehand. But if we need more and more active control and corrections maybe online, that means that we probably cannot predefine these codes anymore. So do we have to move to self-learning autonomous systems in our field as well?
Well, I would get this structure a little bit out of each other. So suppose that you know what your reference trajectory is of the tip, then of course there are standard local loops which make your robot actually perform their task. And in addition, if you measure your end effector, you can use active controls to actually make sure that your robot is doing the right actions to follow that trajectory. So I would call that the local robot controls. And the local robot controls are standard technology, I would say. That's standard control technology from robotics. But that's at the level, assuming that you know your reference trajectory. Your question basically is related to, okay, can we define or can we think about methods to actually design the reference, which is a different question. I can imagine that there will be an opportunity to actually learn from data. So once you have printed one meter or so, you can actually try to have measurements of the accuracy. Not only how did you follow the reference trajectory, but is the reference trajectory indeed the right one compared to the previous layer? And if you can measure that deviation, you can give a correction on top of your reference trajectory. So it's basically a hierarchical structure where you have the local control loops and a larger loop, which is then designing your reference trajectory.
And especially this larger loop, is that still something that we can do as human operators, or might there even be a role for technologies like AI in our field?
So I think data is crucial. There are a lot of examples already where we do these tricks, so to speak. So for instance, in our lab, we have it's not a concrete printer, but it's an ink printer for one of the companies here in the region. It's OC, it's now bought by Canon. They make industrial printers, so also to print surfaces like panels. Printing is basically also a repetitive process. And if you are making one line of color printing and you do the next line, you can actually measure deviation with compared to the previous line. And then you can start to learn from that data, and after a few iterations you converge, and we can make perfect shapes, printed shapes, which are far more accurate than the machine by design could do, and simply by correcting the reference trajectory. And that's called a technique, iterative learning control. It's not simple AI-based data. We actually really use models to make the conversions faster, because you don't want to throw away 10 prints before you actually have a better one. We really want to converge really fast, and that's also what you need in your application field, because you don't want to build 10 houses and then learn from that data, and then the 11th house is then according to spec. That's not what you want.
So you're essentially merging model-driven approaches, simulations, with data-driven measurements.
Exactly. And that's sort of a trend which you can see also in AI literature in general, that the belief we have just in data and in algorithms is limiting. And if you add models, you can have a much higher speed of learning, for instance. Yeah. And also confidence in what your algorithms actually deliver, and confidence about what your technology in fact is doing is also very important. So we call that explainable AI. That's one of the things we are also working on. Yeah.
So up to now, we've seen some examples of very large 3D printers, but instead of bigger and bigger robots, we also see some approaches where a team of small robots works together to make something big. Let's look at an example.
The robot has 2 tracks and the CNC, that the nozzle is fixed on the CNC. The nozzle can go up till 15 centimeters, and this is how we create our first 15 centimeters of the structure. In the front of the robot, we have ultra-red sensor that recognizes the path on the floor, on the ground, and it follows the track. It follows this line, and this is how it prints the first layers.
So this is the second robot, which clamps onto the layers previously printed by the first robot. With this mechanism, it clamps onto those first layers, and then these servos are then rotating the rollers, which is pushing the robot around that already printed structure. As it's going around, the really special thing about this robot is that it's printing on the layers it's already printed. In this spiral that it's printing, it's then constantly going over the layers that it's already printed.
Unfortunately, we didn't have time to show the third robot in this system, but it's actually a vacuum robot that is put perpendicular to the other layers. But well, this seems like a first step towards 3D printing robots that can play soccer in their lunch break.
Yeah.
Is it a development that has a lot of potential for 3D printing on a large scale?
Maybe, yes. I see a parallel with the agricultural industry. So the trend has been for decades to make agricultural machines larger, because people thought, hey, productivity, you need a huge machine on the fields outside to harvest potatoes or whatever. What you see now is what people call pixel farming. And we are doing research on that with my group, and what we foresee is that in a large field, you don't have one crop or one vegetable, you have various things, and the multiple robots, small robots, but maybe 10, and they go all in the field, and they are each of them small, but they can harvest very locally, bring it back, come back. So instead of thinking in very expensive large machines, we think about a multiple of very small machines. What I like about this video is that you could see that the small robot is basically getting its local position information from the fact that it is connected to the piece which is being built. So you have a very local connection to actually the location where you want to be. So no expensive measurement system, what the absolute accuracy is, but the local reference is there. So I can imagine that once the bigger construction has been put down, that smaller robots crawl over the construction and put the things which are relevant.
Okay.
That could be a future.
Nice.
Yeah, interesting. Yeah.
Well, from these small robots is a small step towards drones. I know from some ideas and concept showcases of drones 3D printing concrete, but we already talked about weight. I guess it is an even bigger challenge to bring concrete into the air. Is there a potential for drones in the construction industry?
There's always potential, but for the moment I see drones more relevant in the inspection industry and maybe the small maintenance and repair in the building industry, and not to carry concrete, because I mean carrying a load of a camera is already a lot for a drone, and it's not impossible for a drone to carry a load, but the problem is that the battery is depleting faster, and that might endanger also the productivity of a drone, because if it every time has to go back and charge batteries or whatever. So I doubt about really applications like utilizing printing heads. However, I think for the maintenance and repair business, especially repair is interesting, because then you need sometimes just small amounts of material, and I can imagine that drones might also help there. Yeah.
Reach hard to reach places and so on.
Yeah,
Okay.
exactly. Yeah.
Well, from drones to the construction industry, our industry is often said to be very conservative or slow to adapt new technologies. And while 3D concrete printing might be very new for some, others came up with this technique a long time ago. We have a nice video to illustrate this. Of course, back then, robots were not yet widely available, or available at all. But still, you could say that it took quite some time for these machines to find their way into our construction industry. From your experience in other industries, can you share with us the lessons learned from a digital transformation, the adoption of robotics? What are the challenges in terms of acceptance, risk, and so on?
Let me first comment on this movie. I really like that you found it, and I mean it is about automation. And the interesting thing about this video is that you see that the person still is doing very repetitive work. If you look to it now, we thought, hey, why don't you automate the fact that you put concrete in or whatever he did? So I like that video very much. It is all about being creative, I think. So what is important in your industry, like in all the other industries, is that really people who do the daily work get open in their minds and try to figure out, okay, what could be automated here? What could be an automated system? And for that you have to merge the people who know about automation and the people who actually do the daily work. So I would maybe urge all the researchers in robotics for the construction field to actually also do it themselves, just by hand, and experience, okay, what could be automated here? We should also not overestimate robotics and the impact. I always explain to people, to show them the limitations of robotics. Imagine that your kitchen at home is leaking. There's water spoiling on the ground, and that you want to phone a plumber. Assume that he is a robot. So the doorbell goes, you open the door, there's a robot, and he's asking you, can I help you with your kitchen? And then you have to imagine that this robot needs to come into your house, which is doable for a humanoid robot. But then he has to investigate what the problem is. And he has to estimate what kind of tools he needs and how to open things. If you feel yourself how you would do that as a human, and you imagine that that should be done by a robot, that's far out of reach for the next decade or so to let that do by robots. Why? Because it is a unique task at this moment. It's not repetitive. So everything which is repetitive, you can automate easily because you can program it. You can take some measures to correct it real time with the measurements. So don't overestimate. Look into other industries, like the automotive industry already did automation a long time ago, and try to figure out, okay, what are the pitfalls and the right things there. You still need humans, so think about the combination of humans and robots. I can also imagine that also in your industry, so the robots I've seen up to now for 3D printing of concrete are all focused on performing an automated task. Maybe there might be options and there might be applications also for master-slave systems, where the heavy loading for people can be offloaded because of machines, or where you increase accuracy. So suppose that for some building assignment you need accuracy, or on a distance, or in an unsafe environment, or whatever, then a master-slave option could also be there. So master-slave is often a less big step than full automated robotics. Now, these are a few of the things I would like to mention here.
Okay. So I would like to talk about the role of the government in this acceptance as well. We are hosting this conference from the Brainport region, so we like to work in a quadruple or triple helix with, to bring research into practice.
Yeah.
What is the role of the government in the acceptance of new technologies? Should they stimulate it, and how, or should they even prescribe it?
I think what we have learned, at least in this region, is that prescriptions only work if you want to force a society to really go into a transition. For instance, if we talk about electric driving, you really have to penalize the fact that diesel engines or gasoline engines, they emit too much, and that you need to have legislation to force people to actually move. But in general, I think for new technology, you need knowledge institutes, you need industry, there should be a business model. Henceforth, you also need the government to enable new technologies by subsidies or grants or sometimes legislation. And you need the people. And that's the fourth part. You need consumers, users. You have to include them in this discussion. And then if you all are convinced that the direction is the right one, then you should make a strategy together and then execute. That's what we basically do in this Eindhoven Brainport region, with a lot of dossiers in healthcare, in energy and mobility, all the relevant things nowadays. We address them via this combination of knowledge institutes, industries, government and the consumer.
Exactly.
Yeah.
Okay. And when we talk about a time frame of acceptance and this transition, maybe to make a reference to your own field of expertise, when did you start working on topics like autonomous cars and so on? And how long do you think it will take before these are everywhere? So what time frame are we still starting on?
Yeah, I think that if you show, from your field of application, if you show beautiful examples, that already helps a lot. I've seen beautiful examples here from your group. You have to do different things, I think, than standard. If you print a standard rectangular building, it might be, or it might be not a good business case, but then it is not appealing for others to actually convey the message that with 3D printing technique you can do different things. So I would urge you all to be very creative and design new type of shapes, but also maybe new types of combinations of material. So multi-material printing, integrated smart things into walls, etc. So showcase, make nice showcases and tell the story. So don't stay too long into your own bubble, so to speak, but go out, utilize social media to convince people.
Yeah, I think that's a very important message also to the audience watching us today. In the final moments of this keynote, I would like to go back to your field of expertise. You could say our industry is still lagging behind a bit, so it can be very insightful to see what the state of the art of robotics and mechatronic research is about today. And for that, you have provided us with another video.
Precise Medical Robotics has developed an innovative system to assist surgeons performing vitreoretinal eye surgery. Eye surgery requires incredible precision at the limit of what is possible by hand. Highly experienced surgeons manipulate tiny instruments inside the eye. But with anatomical structures of only a few micrometers, higher precision would be beneficial. Precise employs state-of-the-art robotic technology to obtain this higher precision. The system is designed to integrate smoothly at the operating table and can easily be included or excluded during surgery. To preserve patient contact at all times, the surgeon continues conventional operation with one hand while operating the system with his other hand. Extremely high precision is achieved by downscaling movements and by filtering out the surgeon's hand tremors. Control of the system is intuitive, facilitating easy positioning of surgical instruments.
So what are we looking at here? Is this a development towards completely autonomous surgery?
Now, this is not an autonomous robot. This is a master-slave robot. Basically, it's minimal invasive surgery, in this case for an eye application. You could recognize similar elements like the robots you're using in 3D printing. Now, namely, you have an end effector, which is then inside your eye, and there's a robot arm having that needle which is sticking inside your eye. However, in this case, we have a human with a master device which is steering that robot slave. The feature of this system is that you can scale down the motion. So if an eye surgeon is moving, say, 1 centimeter, we can scale down by our choice via the computer, scale down with factor 10, then the motion inside is 1 millimeter or even go down. The unique feature of this precise machine, which we developed in our group, one of my PhD students graduated on this, is that the accuracy we achieve at the inside of the eye with our needle is about 5 microns, so 0.005 millimeters, which is about 20 times better than the top eye surgeon in the world. And that's amazing because by this machine they can now place stem cells, for instance, behind the retina to cure people with eye diseases. And this is typically where the technology is being used to make the next step for doctors in curing people, which they are not able to do now because they vibrate too much and they don't have the accuracy. So I think that for every application field you have to think about, okay, what in our field we really can do differently because there is technology. And then you can also start to develop the technology so as to really help that specific application one step further. Yeah.
Okay, thanks. I've been really enjoying our discussion so far, but in the meantime, I see a lot of questions have came in via the chat, so I would just like to raise a few of them to you to reflect upon. I see a few on the topic of safety. So how safe is it to have single robots in one place with humans, as we saw in various videos?
Yeah. So there's a whole new line of research now currently being done, which is called cobots. So that's human standing in a production line next to a robot. And safety is the #1 requirement. And fortunately, we have a lot of, nowadays, a lot of sensor technology, different modalities of sensors, which can then detect if the human is too close or not. You can do that with optics, cameras, infrared sensors, radars. So there's a lot of technology where you can have multiple sensor modalities to actually make a very robust system so as to make it very safe. That's a requirement #1. Yeah.
Right. That's at least good to hear.
Yeah. Cobots is the field. Yeah.
Drawing inspiration from the football game, one of the questions, what are the possibilities of using multiple robots in the construction site working coherently?
Yeah, we already discussed it a little bit with the smaller robots. So I think the key thing is that you start to be creative. Don't think only in making bigger things, but also try to reverse the argument. Hey, suppose that we make them very small. We can have them local attached to a surface so that they know where they are. So there could be applications where the smaller robots are more, have a better business case or accuracy and productivity than one big robot. Yeah, because for the price of one big robot, you can maybe buy 20 or 30 small robots. So, but you have to think about from the application and then reason. You have to see the space of possibilities from technology, and then really start with carefully observing what is the real application, and then rethink the strategy.
Okay. One more question. I think this is about the accuracy as well. How important are the weather influences when working on location? Are there any restrictions attached to this?
I can imagine that weather might influence the material and the deposition of material, but I'm not a specialist there. So if it starts to rain, you might have a problem if you don't have a cover. I think windy conditions might influence accuracy, but again, if you measure the end effector, you could partly compensate that by the measurement. However, if it is stormy weather, I can imagine that the frequencies are too high and the excursions are too large to actually be able to compensate that. But in a proper control design of a robotic task, you always think about, okay, what are all relevant disturbances? And for me, weather is simply a disturbance which you have to model. So you have to think about, okay, within this spectrum of weather conditions, I guarantee that this robot can do this task. And outside that spectrum of weather conditions, you should stop or take measures.
Okay.
Yeah.
Well, to wrap up, our journey started with robots playing soccer. We went on to the 3D printers and we ended with high-tech surgery. Can you share with us your main research challenge in your field, which might be the challenge in our field tomorrow?
Yeah. So one of the things is to make sure that if you have an autonomous system, that it understands what it is seeing. So your robots in your field are normally more like industrial automation systems, but we are working a lot on autonomous systems, so both cars and soccer playing robots, etc. But it's very difficult if there are unforeseen circumstances to understand what they actually see. And I always give the example of a car, an autonomous car driving on the road, and at the right side there could be a person, a very thin person who wants to cross the street. There could also be a lamppost. The lamppost will never cross the street. And of course, for the car to continue driving, it is utmost important that the car understands I see a lamppost or a very thin person who wants to. So to understand the rest of the world, that's one of the challenges we are looking into in my group with respect to in the area of autonomous vehicles.
Okay, thank you. So it seems that many of the questions that are present in our construction industry might be answered or have already been answered in other fields. So I guess we have to embrace this technology and also strive for collaborations to bring this technology further. Maarten, thank you very much for being here. I really enjoyed the discussion and for answering all of these questions also of the audience.
Yeah, me too. Thank you.
So that brings us to the end of this part on the main stage. We now have a 15 minutes break and then we will continue with the parallel presentations in the rooms. I hope to see you all there.
Good afternoon. I'm here to present from smart dynamic casting to digital casting systems, or rethinking formwork for concrete structures. My name is Ina Joret-Fritschi. I'm a postdoctoral researcher at the chair of Grammatical Research and at the Institute for Building Materials, led by Robert Flatt at the ETH in Zurich. In 2016, 4.13 million tons of concrete was produced. This is enough to cover England and all its hillsides. This number is steadily increasing due to standard construction, such as these in China, of which 7.72 million units were completed in 2015. To complete standard structures, the overall cost for a formwork comprises up to 53% of the overall cost, which is already a high number. Now, knowing that concrete is reasoning 2.2 billion tons of CO2 to be emitted into our global atmosphere, we might need to rethink the way we construct, which is already being done thanks to digital fabrication and seeing buildings such as these, the O14 Tower by Risa Yamamoto, which was already erected in 2014 with the goal of saving material for the overall structure. So all the void zones that you see are to remove material where it's actually not needed. However, to do such structures requires custom formwork inlays, which in this case was 1,300, which were used one single time. Which reasons why non-standard formworks increase the overall cost of a structure up to 88% of the overall cost of the formwork itself. Now, also knowing the other downside of these non-standard formwork is that they end up as landfill and waste and comprise to the already 36% of construction waste, which is already standing in Europe in 2016. So we ask ourselves how we can reduce. And this has already been asked as a question for more than a decade. Can we reduce material? And can we reduce the formwork? And when we look at the work of contour crafting invented by Professor Kasnevich as early as 2004, we started looking into alternative ways to shape concrete, known as contour crafting or 3D concrete printing. This has excelled into many other new companies and research endeavors all around the world. Others look into stay-in-place formworks, such as mesh mold at Grammatical Research, Aerocrete, or Knit Candela by the Philip Bloch Research Group. While a third adventure goes along the line of looking into 3D printed formworks that are very thin. However, to use such ultra-thin formworks requires an additional support structure around the shell, which is done using sand or additional printed structures around to sustain the lateral pressure of the concrete inside. So these are all very valid ways of looking at how we can reduce material and formwork. But there are other ways, which I'll be presenting today, and that's digital casting systems, which belongs to an additive manufacturing process that aims to reduce material and formwork at the same time. So it started in 2012 with robotic slip forming, which was part of my own PhD in a collaboration with Grammatical Research and the Institute for Building Materials with Robert Flatt. We established a new technology which went into using it for ultra-thin formworks known as eggshell, then for SDC folded structures, and later it converted into AC/DC intense, which I will all be presenting here today. They all have the same thing in common, which is using set-on-demand concrete. And what does set-on-demand concrete mean? Well, in fact, what we do is we have a retarded mix, which is pumpable, and then it's placed into a reactor into which accelerating admixtures are dosed in specific intervals. So for smart dynamic casting, we cast a self-compacting concrete into a mold that moves, while for thin form, such as eggshell and intense, we fill into a still-standing formwork, which is not moving, but for eggshell being printed simultaneously and for intense being supported very weakly. It's very similar to what we do in 3D concrete extrusion, apart from the fact that we are using a self-compacting material that is placed into a minimal mold, whereas they print in a layer-by-layer manner. So if we look at 3D concrete printing, we need a material that is pumpable. Then it needs to immediately obtain strength to sustain its own weight and then sustain the next layers on top. For digital casting systems, we also need a pumpable material, but with the difference of having a material that is self-compacting when placed into the mold, and then building up strength to sustain the weight of the layers placed on top. So I will start to present smart dynamic casting to give you a first overview of how the process works. So this video is one of the first videos taken of a successful production of a column, which proves that it's possible to shape material, concrete material, when it changes from a soft to a hard material. It's worth noticing that we are at that point of time having a retarded mix in a bucket, and then we are accelerating it manually with a stirring stick and placing it into the formwork in a rate set to the hydration of the concrete, which we are measuring offline on the digital penetrometer, which you see in the background. So essentially what we do is to assure that the material is not too soft nor too hard. So if it would be too soft, it would of course flow out, and when it's too hard, we have too high friction, making the structures break. And in between this short moment of time is smart dynamic casting, or digital casting systems. Initially, we tested different rigid formworks to see if it was actually possible to shape this material in this early hydration phase. It was successful, and we were in fact awarded amongst the 5th best innovations in the ETH Zurich with what we call the Spark Award, and later we received the same year the Innovation Award at the conference in Norway. But it was not our goal to shape concrete in a rotated shape. We wanted to see if we could produce material where we optimize, if we can produce material optimized columns, or in other words, place materials where it's really needed. So we started with what we call the local shaping formwork, where we had a 40 centimeter tall formwork in which we placed actuators inside. After some tests, we decided to place the actuators at the very bottom of the formwork to indent the column as we went upwards. To make this a success, we had to make the column hollow due to the fact that we are using a self-compacting concrete that is actually incompressible. However, despite of being able to produce a couple of these tall columns, there was a very limited design space and a lot of issues in terms of friction and slipstick effect inside of the formwork. So despite of having a beautiful image with a beautiful column, we wanted to see if we could go a step further. So instead of only shaping at the very bottom of the formwork, we aimed to test what about shaping all around the formwork itself across the 40 centimeters to actually disturb the material as little as possible inside of the formwork. This was very quickly very successful, and we were able to produce a column which changed from 40 to 10 centimeters and back to 40 in a very short period of time within a bachelor thesis project at the ETH in Zurich. However, changing the cross-sectional area, of course, made it difficult to follow up with the manual acceleration and mixing. Therefore, together with Lex Reiter and a group of students, we developed the concept of a process automation where we used a funnel in which the retarded concrete was pumped in from the bottom and accelerating admixtures were placed inside, and the material was flowing over as a self-compacting concrete into the mold. And of course, all of this in a speed that assures that the batches could sustain their own weight throughout the production. So this success of having a structurally optimized column was the reason why we were invited to take part of the DFAB house at the EMPA in Dübendorf in Switzerland, where 6 different innovation objects were placed together into one unit to prove or show how digital fabrication can actually change the way we build and become more sustainable for our future. It started with the mesh mold and the in situ fabricator, which most of you are familiar with. Then we have the smart slab, and on top of that, the spatial timber assembly structure that was prefabricated at the ETH in Zurich and closed off with a translucent aerogel facade. And finally, the smart dynamic casting mullions, of which we produced 15 individual ones that were reinforced. The fabrication setup that we used was a linear axis, so no longer the 6-axis robot. For this, we again installed a pump that pumped into our reacting system and our actuated formwork, which all together was synchronized in a custom-made software. The reinforcement was probably one of the biggest challenges and novelties of the mullions, since we had never really implemented that in the SDC process. We also had to reduce the cross-section down to a minimum of 7 by 12 centimeters, which of course posed a number of challenges in terms of friction. The connection points of the rebars were used to install them at the fabrication system, but also later on inside of the architectural premises in Dübendorf. So the structural design of the mullions were adjusted to the load requirements of the tributary length of the windows. And these varied across the facade, and therefore the belly size of the mullion also had to. So the red line that you see shows the minimum width of the middle section required by the structural design to take the max deflection that was supposed to be 7 millimeters. So before we started to really do the design, we did some first testing to evaluate the shaping constraints and the mechanisms of the formwork, as well as to enable us to detect faulty productions that could occur during this production. It took quite a number of tests to have a system that enabled us to produce 15 mullions in 3.5 weeks. So the question we were asking ourselves in the very beginning of smart dynamic casting was if we could optimize material usage. And in fact, the answer is yes. With one formwork, we were able to produce 15 mullions that were all bespoke, structurally optimized, reinforced, and saving more than 30% of material. So based on this success, we also established a collaboration with an industry partner called SACAC, which is one of the biggest column producers of Switzerland, who are currently, as we speak, implementing digital casting systems into their premises to replace heavy-duty formworks, as you see here on the image. However, if we take it a step further, we also asked ourselves if we could expand the geometrical possibilities using digital casting systems. And that is how Eggshell emerged. So we saw during the production of the mullions that making a formwork that is actuated and enabling us to shape the material as we are slipping is relatively complex, and it has its own constraints. We would, for instance, never be able to produce a column as you see here on this image with such a formwork. So we asked ourselves, is set on demand with eggshell or ultra-thin formworks could be a novel way of thinking of the formwork. So in a normal classic concrete filling process of a thin formwork, the material would exert pressure and assure that the formwork would explode, as you see on the image. But if you use set on demand, the material is not exerting any lateral pressure on the formwork. And we have a new way of thinking of a formwork, which is as thin as an eggshell, and thereby the name. So the fabrication concept that we developed was to use an extruder with a filament, which is printing as we fill accelerated concrete inside, and all this with reinforcement. We would use a stay-in-place formwork, which could be made of concrete or another material, or a biodegradable recyclable formwork out of a polymer, as done in the PhD thesis of Joris Burger, who will also be presenting in one of the sessions. So Joris had a student project in which he asked the question, how far can we go with the geometry? What is the most extreme we can do, while still including reinforcement? Student came up with the idea of a snake-like column where they printed the formwork while filling it, but also assuring that they made void spaces for post-tensioning cables, enabling them to compile 3 segments into one with post-tension, and showing that the geometry can be expanded significantly with this system. In a parallel study that we did for Basler Hofmann, one of the leading engineering companies in Switzerland, we were asked to produce a column with eggshell to support the non-standard structural roof on the outside of their premises in Esslingen in Switzerland. So this project had to include conventional reinforcement, it had to be exposed to the outside, and it had to take the loads from the roof on top. However, as we were very early in the process with eggshell, and our printing facilities were way too slow, so the formwork you see here took us 36 hours to print, and we could have filled it in less than 6 hours with set on demand. The things were not yet aligned. So we decided to use the set on demand in a separate process. So we started by printing, then we placed the reinforcement inside, and finally we would fill it with set on demand using our manual acceleration system, which we had developed in the past in smart dynamic casting. So you see here the team filling up the formwork, which is only supported to assure that it's not moving around as they are filling inside. So the wooden structure that you see is not supporting any structural loads of the formwork. After the formwork was filled, the formwork is being removed. And of course we have an imprint of the 3D printed structure, but we have no cold joints and we have a beautiful surface. And the final result was then installed on site in Esslingen to provide the first built example using eggshell in a fabrication approach. And in fact, you can read more about some of the constraints that we detected during this fabrication process in the 3D Printing Additive Manufacturing Journal, where we recently published. But we also asked ourselves, can we produce thin folded elements and thereby rethink what the systems can do? And we asked this question first in a bachelor thesis project where the students were asked to produce a canoe that was as thin as possible using the smart dynamic casting technique. And in fact, the students were able to produce a canoe which was 18 millimeters thick with carbon reinforcement, and the height was finally 3.5 meters. So with this concept, we took it a step further and asked, can we replace the heavy-duty formworks needed to produce structural folded elements for architecture. Anna Szabo took this on as a PhD thesis and tested different formworks to see how the design space for such structures could be. After numerous experiments and material adjustments, it was possible to produce a set of thin folded elements. However, it was necessary to manually distribute the material, and the design space was rather limited, both in the possible of shaping and in the height. So this was mainly due to the slow hydration of the material, which Anna Szabo can tell you much more about. In fact, the first prototypes turned out rather as failures, where significant ripples were shown as here in the picture. And this was caused by the increased friction of the formwork, which had an enlarged surface compared to the mullions, for instance. And also a very short processing time of the material that could be shaped due to the fast hydration. So Anna Szabo asked herself, how can I avoid friction? And that is how she came up with the idea of intense formworks. Okay, so Anna went from thin folded concrete structures to intense formworks, which she also calls ACDC, additive controlled digital casting. So instead of moving a slip form vertically, the goal was now to use thin materials that were weakly supported and then filled with set-on-demand materials that used a commercial acceleration system in combination with superplasticizers. And here you see one of the very first successful prototypes, which were actually very fast done. She filled up this more than 1 meter tall formwork in less than 25 minutes. She tested 4 different materials. On one hand, she tested the plastic foil, as you see in the video. Then she tried geotextile and a textile on its own, as well as ram board, as you see in this image. 3 of these were selected and assembled into one single structure. And as you see here, she was also able to have void zones for the post-tensioning cables, proving that very cheap, ultra-thin formwork can be used for the production of concrete structures. So to sum up on this talk, I would like to emphasize on the fact that robotic slipforming, eggshell and intense, as stay-in-place tension formwork, all share the same processing concept of set on demand. And together, they have established a new field of concrete construction and proven that we can use reinforcement systems such as post-tension, conventional reinforcement, and fibers, as well as carbon strands. And this is a new field which we call digital casting, which hopefully will allow us to sooner than later have an impact on both standard as well as bespoke production in concrete structures. And with this, I would like to say thank you for your attention. And of course, I would like to say thank you very much to all the collaborators who've made this work possible throughout the years. Thank you very much.
Good morning, everyone. I'm Costantino Menna from University of Naples Federico II and convener of FIB Task Group 2.11, Structures Made by Digital Fabrication. First, I would like to thank the organizing committee for inviting me to this talk entitled Opportunities and Challenges for Structural Engineering of Digitally Fabricated Concrete. The contents of this presentation are included in the special issue paper published in conjunction with the Digital Concrete 2020 conference and written in collaboration with colleagues from ETH Zurich, Eindhoven University of Technology, Ghent University and Polytechnic of Milan. When talking about the application of DFC in concrete structures, it's clear that DFC affects the pillars of traditional quality control methodology. In fact, new digital processes generates new material performances, which affects inevitably structural design. This turns out with new challenges, mostly related to unknown material properties, calculation input, and also design issue related, for instance, to new reinforcement types. At the same time, DFC opens new opportunities related to the possibility of tailoring mechanical performances and also to improve sustainability of concrete structures in general. Within this context, we have tried to point out the structural engineering peculiarities associated to the safe use of load-bearing concrete structures obtained by Dfc. To this scope, we have collected information from structural Dfc projects developed until 2019, and the resulting catalog consists of 22 structural Dfc projects. Most of the application refers to buildings, houses or offices, but also bridge structures, components or architectural structures. The most frequent technology employed is the layered extrusion, but we also have included examples of particle bed fusion, formwork printing, and also the combination of several Dfc techniques. In the next slides, some structural engineering details of some projects will be shown, and we will try to highlight the connection with the Dfc technology adopted. The first Dfc example is the DFAB house, a collaborative demonstrator developed in the framework of the NCCR digital fabrication in Switzerland, and consisted of a 3-story house built by means of 6 innovative technologies. With reference to concrete structures, we focus on 3 structural elements obtained by smart dynamic casting, mesh mold, and 3D printed formworks. The structural design was carried out without particular difficulties following the Swiss structural design code. In details, the vertical elements consist in slender reinforced concrete facade mullions with variable cross-section, which is fitted with conventional steel reinforcement, including longitudinal and shear reinforcement in the form of stirrups. The connection of the mullions to the top and bottom slabs were designed to avoid the transmission of the vertical loads, and for this reason the design was only aimed to resist to wind loads. With this scope, the structural design provisions were used to verify the integrity of the mullions with respect to the deflection, and also to include the requirements related to the minimum concrete cover. The second structural element of the DFAB house is the double curved wall obtained by means of mesh mold technique. It is a load-bearing wall of 12 meters long and 120 millimeter thick with a double curvature, and it supports the loads of the structural elements above. Due to these characteristics, the structural design was carried out against the value of the vertical load in terms of the cross-section and amount of reinforcement, whereas the reinforcement system consists of vertical continuous bar and horizontal welded segments robotically placed within the edges of the cross-section. The reinforcement was conventionally designed to be compliant with provisions of minimum reinforced content. However, additional material testings were needed in order to characterize the ductility behavior of such an innovative reinforcing system. The third structural element of the DFAB house is the smart slab, obtained by means of 3D printed formwork technique. It is a 78 square meter reinforced concrete slab, which is supported by the mesh mold wall previously described. The slab acts as a double cantilever and carries the 2-story spatial timber units above it. In terms of structural typology, it is considered as a post-tensional structure, having ribs parallel and perpendicular to the supporting mesh mold wall. The shape of this structural element is also optimized with respect to some facade and technical installations, creating some functional voids and also variable cross-section. But even though this particular shape, the element is handled as a conventional concrete structure, but built with different techniques. And also structural provisions are kept the same of conventional ones in terms of concrete cover and also longitudinal and shear reinforcement. In the Future 3 project, a structural 2.1 meter tall concrete column was produced by means of the eggshell technology. This technology allows the fabrication of complex column structures in a continuous casting process, providing similar mechanical performances as conventional built structures. Due to these characteristics, the structural design was carried out by means of conventional procedures and following Swiss structural design code. The column has 8 outer ribs, which acts as a support for the timber profiles. And the only mechanical parameters to consider in the structural design was the global load of the timber roof. Even though the shape was complex, the reinforcing system was used as the conventional one, with the only limit that the reinforcing bar cage has to fit with the formwork geometry. In terms of design provisions, the minimum reinforcement has to guarantee the crack width control and also to avoid brittle failures at cracking. Due to the similarity with conventional concrete structures, no additional tests were required for implementing such solution. Moving to bridge applications, Bicycle Bridge Geometrical in Netherlands is one of the most representative DFC examples due to its successful implementation. The bridge is a post-tensional structure made of 6 concrete segments fabricated by means of layered extrusion technology and then assembled on site. The structural design was conceived to be compliant with the existing structural codes. In particular, the design loads were retrieved from EN 1991, whereas the design values were checked against the Annex D of EN 1990. The material properties used as input calculations were determined by means of an experimental testing campaign at Eindhoven University. The outcome of this testing provided directional dependent compressive and tensile strength data, as well as data on stiffness, shrinkage, and creep. To analyze the global behavior of the bridge, a full nonlinear 3D finite element model was adopted in order to support structural calculations. In terms of reinforcement in the longitudinal direction, post-tensional rods were applied and fed through the openings in the segment of the structure which was printed. Whereas in the perpendicular directions, the reinforcement consisted of an innovative concept of entrained high-strength steel cable. The global verification of the behavior of such an innovative structure was completed by means of the design by testing that is compliant with the Annex D of the EN 1992. In practice, the test was made, the experimental test was made of a mock-up structure of a scale 1/2 in order to check the failure resistance and the failure behavior of such innovative bridge. Still remaining in the layer extrusion DFC technique, the cohesion pavilion recently completed in Innsbruck represents one of the most significant examples of architectural structure. The pavilion consists of 47 unique parts with complex shape, radially positioned and assembled on site according to a predefined geometry. Even for this project, the structural design was conceived to be compliant with existing structural codes, and in particular, according to consequence class 1 and reliability class type structures as defined by the Eurocode. The reference lifetime was 5 years. To make the design simpler, each printed part was designed to be self-supporting. Even though the layered extrusion give rise to very specific mechanical properties of the material, here a more conservative approach was pursued, and the material safety factor equal to 2 was considered to account for the limited experimental data available. The structural design was supported by a simpler linear elastic finite element model, and the outcome of this finite element calculation were used to develop a stress-based principle design of the infill patterns. Moreover, the principal tensile stress coming from the finite element simulations were used as a checking criterion against the tensile strength of the material adopted. In terms of reinforcement, only some reinforcement time were applied to guarantee structural safety, but not to act in tension for the in-service condition. The reinforcement system consisted mainly of carbon fiber reinforced plates to carry the ultimate limit state in tensile loads, but for some particular element of the geometry, also conventional steel reinforcement was adopted to guarantee structural safety. The last DFC project showed in this presentation is the post-tensioned girder developed at Ghent University in 2019. From a structural engineering point of view, the structural principle in this case is very similar to that adopted in the Gemert Bridge in Netherlands, consisting in the layered extruded concrete segments and then assembled on site with post-tension. However, in this case, there are two major differences. The first one is that the 2D shape of this girder was optimized using topology optimization technique. And secondly, the layered extrusion technique was used actually to support a formwork printing process. In particular, the topology optimization aimed to minimize the displacement at the top surface of the beam and also against the post-tensioning tendons. Moreover, the internal cavity of the optimized concrete segments were crowded to create a solid shape. The result is that each concrete segment is a full solid, and in terms of calculation input, an homogenized Young's modulus was associated to the combination of layered extruded concrete and poured concrete. The reinforcement was in such a way a conventional one. In particular, rebars were inserted in the segments and then pre-stressed, whereas the full post-tension was applied to the lower and upper tendons. To complete the structural design, a 3D finite element analysis was required in order to check design values and limits. Moreover, not only the finite element simulations, but also experimental testing was needed to verify and check the deflections and failure modes. From the documented examples, it appears that the issues associated with structural engineering of Dfc projects are handled in a different way depending on the technique adopted and on the overall design approach. This situation was confirmed also by structural engineers operating in practice, who commonly has to face with several questions, such as what is the variation in the material quality, how well are the layers stacked on top of each other, what dimensional variations occur, and also which are the certification and standards for materials adopted in digital fabrication. Of course, the answer is not straightforward, but what comes out is that in this context, the structural engineering has to be explicitly involved in many aspects of the project, such as process control, material production, determination of structurally relevant properties, logistics, and on-site construction. This could help a lot in terms of experience-based rules, which currently are not available for 3D concrete printing, especially with regard to the determination of possible failure modes and also with reference to quality control. In this complex scenario, of course, we at the moment can use two different strategies to improve the handling of the FC project. First of all, the use of three-dimensional nonlinear finite element analysis, both on mechanical thermal loads, can help to replicate the mechanical and physical problem in terms of structural performance. And secondly, in the DFC project, we can also look at some testing which are compliant with available codes, and the outcome of which could be useful to determine calculation inputs and design checks. These two aspects, that is the detailed numerical simulations and the design by testing, are essential to improve DFC reliability in structural engineering applications, especially with reference to the new opportunities associated to DFC. Among the others, topology optimization and generative design seem very promising, but at the same time, further improvements in terms of compatibility with the digital fabrication process need to be achieved. Moreover, also structural design concepts can be suitably developed by means of DFC with several goals. For instance, saving structural reinforcing steel, reducing minimum reinforcement, and avoid brittle failures. There are some examples available with the new structural design concept, in particular how the weak interfaces arising from layered extrusion can be used to reduce crack spacing and crack widths. These are just some examples, but also in this area much research is still needed. From the analysis of the structural DFC projects described in this presentation, it comes out that the target products are mainly represented by buildings, houses, components, and bridge structures. A possible source of inspiration for structural design can be found also in available codes referred to unreinforced or reinforced masonry structures or load-bearing walls, as well as design guidelines valid for precast segmental bridges, which are very similar to those described in the previous slides. Other common features in terms of structural design provisions are represented by the verification of the structural integrity in terms of maximum allowable concrete stresses or maximum allowable deflections in case of reinforced DFC products. Whereas in case of reinforcement included into DFC produced element, the combined action should be carefully evaluated. A common feature is also that the DFC project is commonly developed by means of numerical simulations tool, whereas other topics still remains unexplored. For instance, component joining from prefabricated components has not been handled in many of the projects. It also appears that the reference lifetime for structural design input is relatively short, approximately 5 years. This is probably due to not sufficient knowledge about durability behavior of innovative DFC products. Moreover, also many of the calculation inputs related to material properties are related to extensive experimental campaigns, sometimes coming from academia. But anyway, one of the most significant results that comes out from the analysis of the project presented here is that in most of the cases, the designer can exploit the exceptions of structural codes in reference to innovative construction products or systems. As done for the Gemert bridge in Netherlands, the design can follow the available standards, and in particular can follow some annexes of the Eurocode. So it can follow the design by testing, which is represented in a schematic way according to this flowchart. Basically, the design values are checked by means of experimental testing conducted on mock-up structures, and the results are then verified against the predicted values and against the failure modes observed during the experiments. Given those common features, it's clear that when evaluating the potential of structural engineering in DFC, a highly interlinked scenario must be taken into account. In particular, for a given project, determining the relations between the DFC process adopted, material performance, predefined function, reinforcement topology, and design aspects represents the major challenge up to now. This interlinked scenario points out also the urgent need for new, unified, and effective design to fabrications approaches, including testing methods and regulations. Since 2016, the research community has started many initiatives to develop metrologies, standards, and guidance documents to achieve consistency and harmonization of structural engineering approaches, as done for conventional concrete structures. Here I have summarized the most active international working groups, including RILEM technical committees, ACI technical committees, and also FIB task groups, and ASTM NIST projects. All of them are focused on developing knowledge and standards for fostering the implementation of digitally fabricated concrete structures. I would like to thank all of you for your virtual attention during my presentation, and I also take the chance to thank again all my colleagues and co-authors for providing useful insight and a useful contribution to this topic. Thanks again.
Welcome back to the main stage for the last official part of day 2 of our conference. My name is Lauri Heiss, and I will be leading the wrap-up session today. Before we get to the wrap-up, where I will be joined by 4 scientific committee members, we want to show you a video from our virtual tool block called Science Meets Industry, where we showcase companies that develop new technologies and adapt them in practice. And today, in the 3rd episode, we will be joining the company BAM. Enjoy.
Welcome at Eindhoven University of Technology. Normally our campus here behind me is crowded with 15,000 students, particularly in springtime like this. Unfortunately, due to COVID-19, it's empty now and we can't meet here together in person. At Eindhoven University of Technology, we develop knowledge related to the issue matter of digital concrete. Sometimes in isolation for fundamental research, but most of the time in close collaboration in the Brainport Eindhoven region with our industrial partners. Eventually, all the knowledge that we develop should end up with the industry to accommodate issues like sustainability, construction productivity, and provide a larger degree of freedom in architectural design. Today, we're going to visit the company BAM that realized a unique project with staircases in Amsterdam. And you might know them from the first bridge that they realized here in the Netherlands.
You are at one of the sites of BAM Infra. It is part of the biggest construction company in the Netherlands and works abroad. And this place is the Oude Kerkelaan in Amstelveen. We started with digital concrete because it fits in our strategic agenda of BAM Group, building the present, creating the future. For us, it helps in being more sustainable, work innovative, and do a flawless process. If we do things digital up front, by engineering, we also needed to do it in the construction site as well. It all started in Gemert with the first 3D concrete printed bridge. It opened in 2017. We actually used the facilities of the TU Eindhoven to produce it, and we worked close together with also a client and all partners that were involved. It was a major step in bringing technology from the research center into the real world. And for us, it was the first step of printing with concrete. We did a few tests before we actually printed the bridge. If you introduce innovations, it's important that you involve all the stakeholders every step you take. We worked closely together with the local authorities from the start of the process. They were able to check every step we took to be sure that they would get a reliable solution. Because it was complete new, we had go, no-go moments in the planning to make sure that if things could go wrong, a regular bridge could be put in place. We used some reinforcement in the bridge in Gemert. It was put in place during the print process by putting a cable in the layers we printed, and also afterwards when the elements came on site, they were mounted together with a post-tension strange. The design was made by Witteveen & Bos and based on principles of our BAM structural engineering and the knowledge of the researchers of Theo Salet. The complete process followed the Eurocodes, which has the possibility to meet the regular requirements, but now proved by design by testing. So during the process, we tested the model on its maximum strength at the TU, and on site we did a load test. We learned a lot at the Gemert Bridge, but one of the major things is that we can use less material in the same structure. And it was a little bit over-dimensioned in Gemert, but we see now that we can reduce material for at least 40% as you compare it with regular concrete elements. BAM and Weber BMX joined forces and opened a 3D concrete printing factory in Eindhoven, which was opened last year. In this factory we are able to make bigger objects so we can scale up the ideas we have on 3D concrete printing. So in the factory we were able to continuously learn about 3D printing and how to use it in our projects. The first things we learned in our factory is that we can use mortar with a higher strength and also use different types of reinforcement during our process. At the Oude Kerklaan, we use a parametric design which was built by Witteveen & Bos, one of our partners. And with the parametric design we were able to build different sizes and use the same digital design. What you see here are stairs that are an exact copy produced by a robot coming from a digital design. So we make use of all the knowledge we gained from Gemert, but also from the stairs, and we all bring it together on several elements in our projects, such as objects like a flow system in Driebergen sized, 3 elements, we put it in place, and also on this spot at the Oude Kerklaan we have some elements printed. So we learned a lot from the 3D printing technology, but we're not there yet. There's a lot new to come. And we are looking for opportunities where we can use this technology in projects. Eventually, we also want to print on-site and bigger objects. So we need to work together to make that possible in the near future. So if you have good ideas on 3D printing, please contact us and we would like to collaborate with you.
Welcome back. I hope you liked the video and found some inspiration to further strengthen the collaboration between science and industry. Let's now move on to the wrap-up session. We are joined by 4 scientific committee members who were divided in different presentations today. We are now joined by Professor Victor Mecheterin, Professor Richard Boswell, Dr. Wilson Ricardo Leal Silva, and Dr. Arnaud Perrault. The scientific committee members we have here today have kindly agreed that I call them by their first name when addressing them. So yeah, let's get started, I guess. Victor, I think you were mostly looking at session, or room A, I should say. Can I get your impressions and what did you think about it?
Okay, yeah, hello everybody. So I'm really glad to be able to say a few words here. So actually really amazing the second day of the conference. Perfectly organized, extremely interesting, very good mix of fundamental research and also presentation of engineering solution to the challenges posed by the new technology. So what I liked most actually is the fantasy and boldness of presenters, trying different approaches for achieving the goals. Actually, there were two sessions in the room A. The first one was on mixed design and binders and admixtures. And we saw here some interesting approaches on alternative binders, like using iron-rich slag, geopolymers. And I feel that we have really here a good possibility, not just to make the system sustainable, but also to improve the technology. I mean, to provide some solutions for steering the processes. I think there are a lot of potential there also, of course, in other alternative binder systems as LC3 and others. And then, of course, we need adequate construction chemicals for the new binders. And we also need some new approaches from construction chemicals also for existing binder systems, such as cement-based systems. So, and this, again, some topics presented today. And finally, I want to address one presentation where it was the accelerator what was applied directly on the printed surface. And for me, it was really a surprise that really good results can be achieved. So it means the boldness pays off in such a project. So the second one, it was on structural engineering and reinforcement, the second session I attended. And well, reinforcement is obviously the key issue. And so there were two interesting approaches on this. In one, using screws as a reinforcement, steel reinforcement, another one using kind of a combined approach based on use of textile, short fiber, maybe some other alternatives. So both ways are certainly interesting and good to follow, but they are actually just examples for the variety of different solutions we have here. And finally, there were two really very interesting talks on the structural level. So it's mostly about testing structural elements, also topologically optimized. And such tests are really very, very important, both for purposeful structural design, but also for material testing we need to apply in further research and then praxis. So yeah, again, so a great day, very interesting. So we see that 3D printing and other digital technology really push many topics forwards. And I'm really looking towards the next 2 days. So thank you so much.
Thanks, Victor. That's nice to hear about the screw reinforcement, especially. Okay, let's move on to Richard.
Okay. Hi. Yeah. Thanks. So I was lucky enough to be in room D today, which was based around presentations on digital design technologies and industrialization. We had two great sessions, excellent presentations all around, and very engaging debate in the chat rooms afterwards. So I think what I did was have a look at the sort of themes that I felt were running through the presentations in the session. And I think one thing that came through is ambition. And this is that we're no longer trying to print simple concrete parts, but actually that realizing the full extent of architectural, the freedom that the printing allows us to do. Obviously that if we want to realize the full potential of digital fabrication methods, then we need to look to how we can utilize the forms in the best way. And I think this was particularly highlighted by Pablo's presentation, which was really looking at the application of performative architecture and the fact that when we can do things in a bespoke way, we can make those make our designs for the built environment more effective, which I think is really important. And also highlighted, you know, the way that digital fabrication is going to make these things a reality. I think also Romain Duboulay presented us with his space frame that he's been working on, which is a combination of how you can use 3D printing to generate a really three-dimensional structure. So this is not printing in layers. This is actually printing physical lattice structures, and he developed a wall technology that actually had an insulation in and a structural aspect to it as well. What I think is really interesting is that now we're not just talking about 3D printing, but we're talking about 3D printing with other processes. And what Romain did was to use hot wire foam, computer-controlled hot wire foam molding to generate a piecewise system that would be built in sequence with the printing to allow this more elaborate space frame geometry to be printed. And this was also reflected as in Guy et al.'s presentation, who were looking at how you can mix different digital fabrication methods to generate more aesthetic components that could fit together and perhaps allow ways in which to build in more function and more form. But I think key is that they're both pointing to a way that the ambition now is needing us to actually look outside and beyond one single process. And I think there's going to be a whole bunch of interesting work as people start to combine these going forward. Of course, the design of these things, the more complexity we have, the greater role there is of computing. And there were a number of presentations that highlighted the effectiveness of and use of computer modeling. And Eduardo's presentation was looking at how you could then use clever modeling to understand how to design fabric-based formwork. And there, of course, is if we can utilize the structural capacity of the material efficiently, we can reduce material, which has a real strong resonance with sustainability. But also, Changzi was talking about the modeling of wet material, understanding how these, how we can do this and how we can improve, which also Raphael also talked about. And it all echoes back, I think, to what Robert was talking about in the opening session, about understanding how we can model these things better and how modeling is going to help us build. And I think particularly this has run through for me yesterday and today. It really starts to lead us towards robustness. And you know, these modeling techniques are going to start to allow us to explore complicated geometries and be confident that they can be built. And what I think we're seeing here, as well as Stefan's presentation, where he was starting to talk about testing methods, looking at how you can generate design, how you can generate to understand processes better. I think it's all starting to point to an area where we need to start developing testing methods that are more systematic, that allow us to assess the process capabilities better in order to raise the bar of what we're able to manufacture. Thank you.
All right, thanks. Yeah, let's move on to Wilson.
Yes, I had the pleasure to join Room C, which was all about mechanical performance, the two parts of the sessions of the day addressed that. And it just struck me not by surprise, because it's by the end of the last Digital Concrete conference in Switzerland, we kind of were just gathering after the event and just think, okay, there is a very high likelihood that there will be a lot of research papers coming up towards investigating the use of fiber reinforcement on 3D concrete printing. Then within this session, 5 out of 8 papers that were presented were addressing how to increase ductility of printed elements, whether it's from a fire resistance standpoint or mechanical standpoint. So these were very interesting presentations and very well distributed geographically. It goes all the way from France to South Africa. So very interesting papers, and I should certainly have a deeper look into them, the content within the proceedings of the event. And the two other papers, or three, addressing mechanical performance from a matrix, like a cementitious matrix standpoint. One was from Arnesh, that was quite interesting, from ETH Zurich, studying the influence of process, and specifically the extrusion process and pumping process within the pore size distribution, like air inside the matrix of the material that's being extruded. So very, very nice research paper by Arnesh. And then there was Malek from, Malek, I don't recall exactly the institute, I'm sorry. My notes are scribbles here too. But he was working on the development of a high performance concrete that is lightweight, so for installation purposes, and talked all about the mix designs that he was working on. They didn't go all the way through doing a full print, but it raised a lot of questions, and then he was quite well articulated on commenting on the challenges of using a lightweight or developing the lightweight aggregate, and then some ways to overcome some of the challenges in his process. And last but not least, Lorenzo presented on the mechanical characterization of early age strength development, including the effect of creep, which is quite interesting for those who want to know more about strength developments, E-modules, evolution, accounting for creep. And then it raised quite a lot of questions on measurement methods, time dependence, and how fast is running the test, and what is the so-called time zero of your test. So I do recommend watching that one if you are still online and want to rewatch some of the presentations. So check room C. These are my thoughts.
Thank you, Wilson, for that update on room C. And last, Arnold, can you give us something? I think you were in room B.
Yes. First, I want to thank you and congrats the organizing committee for this really nice event. This afternoon, I see in room B8 very interesting and different presentations. All are dealing with the rheology on the fresh state behavior of cementitious material. I'm quite happy to see that many things have been done since 2 years, since the last digital concrete conference. There are quite some new things. And if I try to summarize what I've seen in 3 or 4 points, I will first put the need for the description of the time-dependent behavior on the strength development of the cementitious material. It is really needed in order to optimize the printing rate or the construction rate, depending on the process. And there are 3 different presentations, the one of Stefan Grunewald, the one of Laura Esposito, and the one of Ilan Marbuz, who are dealing with this point. Secondly, I will list the description of the elastic behavior of the material. This is a key point in order to prevent the material from buckling during the process. And the presentation of Laura Esposito, Ilan Marbuz, and also from Johan Jacquet deal with the description of the elastic behavior. Third point, on what I found to be what is really new during this conference is the description of the tensile behavior of the fresh dead cementitious material. There are 3 different presentations among the 8 who are dealing with the problem of cracks formation during the printing or during the flexible mold process also. And it's very important to describe this tensile behavior in order to avoid the formation of cracks during the process. And I think it is really new. And yesterday there was also a presentation dealing with the tensile behavior measurement of Nicolas Ducolombier, and I think that will be a new topic for the rheology of printable cementitious material. And last point, I want perhaps to also add the word sustainability, because we can see that some authors and some presenters, the Alassane presentation, for example, try to incorporate new type of material like dune sand And also the presentation of David Fagliano deal with lightweight concrete. So he wanted to provide some insulation properties to this material. So to summarize, I see time-dependent behavior, elastic behavior, tensile behavior, and sustainability. This is the 4 key points I see from the presentation of today.
Okay. Yeah, thank you. Thank you for that, Arnold. And with that, I would like to thank the scientific committee. Is there anything that someone from the panel wants to say something? Any comment or? No? Okay, in that case, I would like to thank you again for looking at the presentations and giving us the summary. And with that, we're about to end the stream, but do realize that even though we are ending the live stream, the conference day is not over yet. Please use the facilities that are on the Hopin platform, like the breakout sessions or one-on-one communication possibilities. You can do that through the evening up to tomorrow morning when at 9 a.m. Central European time, we will have the day 3 go live at Hopin platform, and make sure you use the ticket for that specific day and join tomorrow's presentations. And with that, we're going to end the live stream. I hope you have all enjoyed today's presentations, and we will see you all tomorrow.
Welcome at Eindhoven University of Technology.